see it on the preview? Oh, yes.
So we look pretty much for your ride home.
Okay, I'll turn it off.
All right. So our next talk will be. So our next talk will be by Brian O'Malley from USGS Great Lakes Science Center.
Thank you. So today I'm going to talk to you about two different methods that we're using to sort of assess coregonine morphology and actually trying to compare and sort of tease apart some of the differences. I'd like to sort of start off by acknowledging my co-authors, especially Randy Eschenroder. For those of you that know him, I mean, you know how relentless he is with some of his taxonomies. So he had this idea and sort of pitched it to me, and I've sort of been running with it lately. And then Chris Olds and Andrew for providing a lot of these fish that we use in this analysis. So to sort of set the stage, I just want to start with this quote from Lewis Carroll's Through the Looking Glass. I'm not going to read it, but you can. Basically, Alice and the gnat are having this conversation about sort of the gnat is questioning why use names to sort of distinguish different species. And Alice points out that it's useful to the people that name them, but not necessarily useful to the species themselves. It's a human construct that we use. And so, you know, you might have heard these terms, lumpers and splitters, where you can have sort of two different camps, where splitters like to sort of, you know, keep dividing and dividing and making more subspecies and everything like that, whereas lumpers are the complete opposite. But I think ultimately, as scientists, it's sort of some sort of sweet spot is where we want to be, in the middle of that. Okay, so for background, I'm going to refer to traditional morphometrics as sort of linear measurements, and these are historically what's been used to sort of separate species. You saw in the last talk, the hour key was morphometrics, what, you know, sort of the whole key is based on. So these are linear measurements, and the sort of way to standardize them to account for some of the allometric and size effects are to sort of take them as a ratio. So you can have body depth and you divide it by standard length to sort of account for the size of the fish. But these aren't really informative of shape per se, so you don't actually capture anything on the outline of the fish. You know, if you have a fish that's deeper body, that's really has a different arch, it doesn't capture that. So that's in contrast to sort of the newer technique is geometric morphometrics. So this is shape analysis. And so you can see in the picture there that there's landmarks placed on the blue points. Those are at homologous structures, so at the start of a fin. And then also the purple lines are actually the curves, so that we trace them around the outside edge of the fish, and then you can extract the points from those. And so this results in sort of a coordinate space you can see here, like so you can have X and Y coordinates and interpret shape that way. So within the Great Lakes, if you heard some of Trevor's stuff earlier, there's a species flock of different coregonines. And so with the exception of blackfin, which is the fourth one down there, that's from Lake Nipigon, there's basically 4 different forms that are still present for ciscos. And that's, the type form is Artidae in the top there. And these have been separated based on traditional morphometrics, historically by Celts, but also Gilrick accounts and different ecological differences like depth and diet. And there's already some forms that we think we've lost. So there's 3 forms here. So that's why it's important for us to keep understanding this diversity before we lose it entirely. And that's sort of what's known as the coregonine problem as well. These are a group of really phenotypically plastic species. And this is an example of European whitefishes. So they have a similar coregonine problem over there, where it's a sort of bewildering array of different morphologies. It's hard to sort of make sense of it. Whereas, you know, some people say in the Great Lakes we have this C. artidae complex. Whereas others say, well, no, there's actually different morphs that can be delineated based on form and possibly even function. So what I'm going to focus on is mostly within cisco or coregonine artidae. There's sort of 4 main forms that we can sort of accept, where there's the typical artidae form shown at the top, and that's sort of it's characterized by having a slender body, And then short head, which is the new one that Randy has a paper coming out sort of describing it, where it basically has a shorter head, also slightly deeper body. Manitolinus and albus, the last two ones here, they're sort of characterized by more of a deeper body. Manitolinus has this really short caudal peduncle. You can see the adipose fin there is really closer to the caudal fin. And albus is, probably has a smaller head, but also someone mentioned scale counts earlier. Albus is said to have less scales along the lateral bottom. And the sort of reason for doing this work is that across all 5 Great Lakes right now, there's this sort of effort to sort of understand and provide some science to help with cisco restoration or coregonine restoration in general. And we're sort of up here in these 2 orange boxes right now. So the first box there, resolving some of the taxonomic issues. That's sort of where this project has been going towards. So the objectives of this talk are, like I said, to understand some of the trade-offs between traditional and geometric morphometrics, with the goal of trying to help inform some of these taxonomic issues going forward. Look at different differences in sensitivity between the 2 methods, and look at some differences in geometric landmarks, so differences in curves and landmarks separately, and then how each method might perform in a mixed sample, and ultimately try to provide recommendations for moving forward. So I used 6, I'm going to call them just kind of groups for now, where I threw in Chameau Bay population, so it's not actually like its own morph or anything like that. It's sort of thought to be mostly typical Artidae, but there are some potentially deep-bodied forms in there as well. We're not sure, but just treat it as a mixed sample for now. And then the next 2, coregonine hoyi. So this is sort of used as a control in this case. So it's a bloater. This is not coregonine Artidae. It's a bloater. It's its own species. But I've used them from collected from deep and shallow toes. So as its name suggests, it tends to bloat when it's brought up from depth. So this is sort of, we're going to try to look at some of the effects of bloatedness with this and how it might have like an artifact on shape. And then the 3 other morphs that I took from paper that Randy. Here's just some collection info. So for the most part, they're from samples from Lake Huron, provided by Randy and Chris Olds and Andrew. And then, like I said, Chameau. And the only thing I always want to point out is the difference in size here. So like I said, with traditional morphometrics, you run into issues with size if you don't correct for it. So, and then here's the depth capture differences. So the bloater collected that we're calling deep, they were collected from 70 meters mid-water trough. And then shallow is a little shallower. All the cisco forms were collected from much shallower gill net sets. So I used 9 different morphometrics, and we also have total gill raker counts, but I'm not using those. This just focus on morphometrics. In total, 152 fish were processed. These were fish that had image as well as the measurements, but then we dropped out some of them because of, say, broken fins or bad images. So in total, 143 fish. Converted morphometric measurements to ratios, as typically used, and then also applied a size correction to try to account for some of those size differences. I'm not going to go into the details about the size correction, but if you have interest in hearing about that stuff, talk to Yu Chun at Great Lakes Science Center. He was the one that sort of really dove into some of the differences in those methods. For geometric morphometrics, we use stereomorph, which is an R package, and I found it to be super easy to use. I highly recommend it compared to some of the other packages out there to use. So we chose 14 homologous landmarks and 2 semi-landmarks, and then, like I said, also drew curves along the ventral side and the dorsal margin, and then extracted points from those as well. For data processing for GM analysis, we, after digitizing, we then subjected the data to Procrustes analysis, so that accounts for differences in rotation, size, and scale. And I performed both of the analysis for just the 16 landmarks, and then also the landmarks plus the points extracted from the curves to see if adding the curves helps. And then we did differences or different multivariate tests, so PCA, CBA, and here's some of the packages used for that in our. Okay. So first I'm going to show this is a PCA of the sort of raw data, the traditional morphometrics, these are the ratios, but this is without the size correction. So one initial question we had was, would size correction, does it matter? Does it help with the interpretation of the data? And so, as we expected, the POI, which is the bloater that we thought were a single morph, but just collected from different depths, the sort of null hypothesis there was that they would be well overlapped because they're one species, not to be one morph. So it looks pretty good there. And then you see with some of the other artidae morphs, so Manitolinus, shorthead, typical artidae, there's some overlap, but overall some spread as well. And now this is, again, same graph, but now with size correction applied. And actually, if you look at the, say, the first principal component, it really didn't change all that much with size correction added. So it suggested, it was kind of surprising that we thought we'd actually account for much more variation once we adjusted for that. Still see that both bloater forms are still well overlapped. Not much difference there. And overall, displaying a pretty good amount of variation, 60%, the first principal component. So for the geometric morphometric analysis, now is where you start to see differences in the bloater. So whereas this POI collected really deep, these are the ones that were bloated. You see that they start to spread apart from the shallow morph. The ones that were collected shallow. And along this first axis, you see the differences in shape are really captured well. So this first axis driven by differences in the dorsal margin, where on the far left side you have a much steeper dorsal arch, whereas on this far right end you have a much flatter dorsal arch, and obviously differences on the ventral margin as well. And overall, compared to the last graph, you see a lot more scattered. We're explaining a lot less of the variation, only 39% in the first principal component. And so this is with the 16 landmarks plus the ones that we extracted from the curves. And I should have pointed out that the gray here is the mean overall shape, so that'd be like the mean right in the middle, and then the black is the reference. Okay, so now this is just with landmarks without the points extracted from the curves as well, so it's just the 16 landmarks. Explained actually slightly less, so that's what we expected. We were expecting to explain more with the curves added. Much wider overlap between all the groups. Maybe slightly more overlap now with the two different bloater forms or groups. So the question, the forms that we had from the traditional morphometrics, they were significantly different based on traditional measurements. Randy used the ANOVA approach. So the question that we had was, are there differences also detected in mean shape among groups? And so using an ANOVA, Procruste's ANOVA said yes. And then so we said, okay, well, next step is what about pairwise comparisons? And yes, using this F-test method, every single sort of pairwise comparison in this case was significantly different, which doesn't quite make sense, and it might be a false positive for, say, something like the bloater. We're expecting this to not be significant because it's thought to be a single morph. And this procedure was again repeated for the 16 landmarks plus the 20 semi-landmarks that resulted in this exact same result. So now we use a CBA approach, which you're allowed to basically have previously defined groups and then see if they statistically fall out into those groups as well. And so for this, we use the previous assignments that I showed earlier. And again, another table. I know it's not very pleasing to look at tables, but I'll just highlight. So the way you read this is that the first row here would be the a priori assignments, and then what you're expecting is if they fall out perfectly into your groups again, there should be, for example, this Chameau Bay, you should see 29 here, and then all the zeros going across, right? So you can see in this column, there are a couple that didn't fall out in any of the groups afterwards, or there might be some that were misplaced. So for shorthead, 2 were reclassified as Chameau Bay, and then shorthead 2 or 25 were classified as shorthead, and 2 fell out. So this is with the 16 landmarks plus those with the curves. And so what was kind of concerning was that we weren't able to, we had 5 that were there that fell out. And then again, repeating that analysis now without the curves. In this case, now we only have 1 that wasn't able to be replaced. So for conclusions, so we had a much higher amount of the variability was explained in our principal component analysis using the traditional morphometrics, which was sort of counterintuitive to what we thought. We thought, based on some of the stuff that we've seen in the cyclic literature, that using geometric morphometrics would actually explain much more. That didn't seem to be the case for this. And you see in the geometric morphometrics, there's much more overlap between Manitolinus, which is one of the deep-bodied forms, and Shorthead, which is also a deep-bodied form. So that's interesting, maybe that there's other differences that are better explained between these 2 morphs using a traditional approach rather than a shape analysis. Inclusion of the curves did explain more power or did have explained slightly more variation in the GM approach. And like I pointed out with some of the differences in bloater, that was sort of our control where we had the shallow and deep, and there should be still 1 morph. They're actually starting to separate out, and it might be like a false positive for identifying morphs. I didn't incorporate albus, but that's not to say it's a goldfish. It's just one of Keltz's historical specimens, and that's been pickled for many years. The next step is to then try to see if anyone has any albus data that we can throw at this as well. So a couple more trade-offs to consider between these 2 approaches that I didn't quite touch on here. That traditional methods, you're often taking very careful measurements and usually requires killing specimens. So with a geometric approach, you can more easily just take a picture as long as it's done well. You have to account for distortion if you're going to not take a good picture. So it's important to really take a good picture and follow some of the methods there. But it can be a much more rapid method to data collection than actually killing the fish. So we're still working on resolving all these different recommendations for these 2 methods for coregonines, but the initial one that I can pull out is just taking the picture and using images. It seems to be an easy approach. And what I'm not going to show here, but I have, is we did also extract linear measurements from the pictures as well, and obviously well correlated. You do start to see less agreement as you get towards the head and take small measurements towards the, say, maxillary bone or the eye. So that's the sort of next step as well, is trying to actually make sure that if you can just take a picture and it's much more reproducible, why spend time measuring stuff in the lab? I think that's all I have. Real quick before I take any questions, I'm relatively new on the landscape here, so if anyone's interested in collaborating on anything, I'm at the Lake Ontario Biostation. Always open to talk about anything, from mysis to vertical migration to fish and food webs. So, thanks.